Hello everyone, my name is Quentin Pan, and my team is going to introduce a method to give POI recommendation, which is called SAE NAD. As the development of the mobile device and location acquisition technologies, accessing a real-time location information is being easier and more efficient. Because of this development and the convenience of accessing real-time location information, the location-based social network became an important part in people's life. Imagine that you are sharing your experience on a location, such as restaurant, museum, parks, etc. on the internet. This location point in the map can be seen as point of interest. Point of interest, which has a short form POI, can usually be seen in some software such as Google Maps, Yelp. Due to the popularity of the software, there are a huge amount of user POI interaction data, and this data can be used to train a model to provide personalized POI recommendation. Some topics in machine learning, such as classification, clustering, can be used to train model to give a POI recommendation to users. POI recommendation is an important topic in the domain of recommender systems. Here is an example for POI. This is a screenshot from Google Map. When you click some location in the Google Map, and you can do some steps to get recommendation for more locations that you might interested. For example, in this screenshot, I let the map know I want to know the restaurant nearby, and these red points are the restaurant that near the university, and these locations are the POI that Google Maps provided. This paper will introduce a novel autoencoder-based model to learn the nonlinear user POI relations, which is called SAE NAD. SAE means self-attentive encoder, while the NAD means neighbor-aware decoder. Both of SAE and NAD includes the knowledge in machine learning. In the previous works, the method is just equally treating users checking POIs, but in the proposed method, the SAE adaptively differentiates the user preference degrees in multiple aspects. Some other relevant personalized POI recommendation methods, such as matrix factorization, can often be seen. Some famous software, for example, Netflix, use model-based methods which are built on matrix factorization. Some methods that based on matrix factorization will be used as a comparison with proposed method in this paper. Next, we will focus on introducing the proposed method in this paper. Here are the important notations that need to be noted before introducing the proposed method. For example here, X is the input data, and X hat is the reconstructed data. W star is the weight matrix, and B star is the bias vector. W star and B star can be got by using the proposed method. Before introducing proposed method, let me introduce what is an autoencoder first. Single hidden layer autoencoder is an unsupervised neural network which is constructed by encoder and a decoder. The encoder contains one activation function that maps the input data to the latent space. And the decoder also has one activation function that maps the representation in the latent space to the reconstruction space. Here are the formulas of the encoder and decoder. We can see that X is the input data here, and weight matrix W, bias vector B, are the elements that we need to train from a training data set. In the encoder, the output Z is the representation of X in the latent space. In the decoder, let Z be the input, and the output X hat are the reconstructed data which we need as an output. In this paper, The dataset are got from Goala, Foursquare, and Yelp. All of them are famous software that can let users share their experience, and this data can use to train a model. After the model be trained by the proposed method, this paper also compared the performance of different methods in POI recommendation, and the comparison result will be introduced later in this video. This is the whole view of the proposed method, SAE-NAD. The yellow part is the SAE. SAE use single hidden layer neural network without bias to compute important score. The green part is the NAD. We can see that NAD use RBF kernel, which is relevant to the material in STAT 441. NAD use the RBF kernel to make checking POIs exert more influence on nearby unvisited POIs. And next, Hao Chen will focus on the detail in SAE NAD.
Thank you, Tony. So next, I'm going to talk about the details of our algorithm. So the purpose of recommendation neural network is to find a way to increase the visit rate of our recommendations to users. At the beginning, an attention model is adopted to measure the relevance between users and atoms. After the power of CNNs is discovered, CNNs are used to model user preferences and atom properties with dual local and global attention. The local attention provides the insight on a user's preferences or an atom's properties, and the global attention helps CNNs focus on the semantic meaning of the review text. However, the method introduced in this paper is a little bit different. The structure of the network in this paper includes a self-attentive encoder as the input layer and a neighbor-aware decoder as the output layer. After applying these two layers, the performance of the recommendation network is improved dramatically. So the structure is shown here. The model is contain three parts. As we can see, the left, middle, and right, showing different colors. The structure is very similar to what we've learned in STAT 441. So the layer in yellow is the encoder layer. It transforms the performance vector of POI into hidden represented data using the weight W1. And the layer in green is the decoder layer. It transforms the data in the hidden representation into recommendation using the weight W4, which is in green here. So I'll explain more clearly in these two layers. So the self-attentive encoder is the input layer. Its goal is to adaptively assign different importance on checked-in POIs for expressing various users' preference levels. To explain further, the input is a preference vector XU, contains 0 and 1, and it indicates whether the user has been to a certain POI. The weight WLU isn't selected based on the vector, and after that, the activation function, which we learned before in the STAT course, softmax and tanh, both functions are performed, and we get the user hidden representation AU, which is shown in the equation here. And so, however, only assigning one single importance value on a POI is not enough, because the users can visit a POI for many different reasons. Like, for example, if I go to a restaurant, I will probably go there because they have good food, or they have good service, or some excellent environment. So those are very different features. So an attention layer is introduced after the decoder. The layer is contained in WA, which is here. So let's talk about the neighbor-aware decoder. POI recommendations has a well-known phenomenon. It's called the geographical clustering phenomenon. It's not hard to think that users prefer to check in POI surrounding the POI that they visit before. So a check-in POI may have impacts on other unvisited POIs. For the intuition of that, we apply another weight WT in the output layer. Finally, an aggregation layer is added to the networks to aggregate users' representations from different aspects into one aspect. So here is our objective function. So normally we minimize the function, and the partial derivatives with respect to all the proper parameters can be computed by gradient descent with backpropagation. And after that, the training is complete. Next, Sarah will talk about the comparison between the algorithm in this paper and other algorithms, and show like how our algorithm is better than others.
All right, thank you, Hao Chen. So I'll take it over from here. All right, so now let's kind of dive into how the authors kind of comprehensively evaluated their matrix. To obtain a comprehensive evaluation on the effectiveness of this model, our authors performed a thorough comparison between the proposed model and existing major POI recommendation models. These methods can be further broken down into three main categories. The first one being traditional matrix factorization methods for implicit feedback. Second one is the classical POI recommendation methods. And lastly, we have the deep learning-based methods. Here, these three key evaluation matrices were introduced as precision at K, recall at K, and map at K. I'll talk about them in a short while. Through comparing all models on three datasets using these above matrices, it is concluded that our proposed model achieved the best performance. So to better understand our comparison result, it is critical for us to first understand the meaning behind each evaluation matrix. Suppose our proposed model generated K recommendations based on the POI algorithm for the users. Our first matrix, precision at K, measures the percentage of the recommended POIs which the user has visited. Then recall K is also associated with the user's behavior, but it will measure the percentage of recommended POIs in all POIs which has been visited by the user. And lastly, map at K represents the mean average precision at K, where average precision is the average of precision values at all K ranks, where relevant POIs are found. Among all models in our comparison group, RankGeoFM, IRNMF, and PASS produce the best results. Nonetheless, these three models are still incomparable to our proposed model. The reasons are explained in details as the following chart. Both RankGeoFM and IRNMF incorporate geographical influence into their ranking models, which is significant for generating POI recommendations. However, they are not capable of comparing nonlinear interactions between users and the POIs. In contrast, the proposed model, where they incorporated geographical influence, adopted a deep neural structure which enables it to measure nonlinear and complex interactions. As a result, it outperforms the two methods in the comparison group. Moreover, comparing PASS, which is a deep learning-based method, The proposed model offers a more precise measurement on geographical influence. Though PATH is able to capture complex interactions, it models the geographical influence by a context graph, which fails to incorporate user reachability into the model process. As a result, our proposed model is able to outperform this proposed PATH method by capturing geographical influence directly through its neighbor-aware decoder, which allows it to achieve the better performance overall. In summary, our proposed model, namely SAE-NAD, clearly showed its advantages compared to many state-of-the-art but baseline models. It is self-attentive encoder, effectively determines user preferences on tracking POIs, and its neighbor-aware decoder measures geographical influence precisely through differentiating user abilities on unvisited BOIs. By leveraging these two components together, it is able to generate recommendations that are highly relevant to its users. And besides developing the model and conducting detailed analysis, our authors also did a very good job in constructing this paper. The paper is well written and has a high logical structure. Definitions, notations, and matrix are introduced and explained clearly, which enables our readers to follow through this analysis very easily. Last but not least, both the abstract and the conclusion of this paper are strong. The abstract concisely reported the objectives and outcomes of the experiment, whereas the conclusion is sufficient and precise. So this is why we picked this paper and presented to you. We hope you all enjoyed it and learned something. Thank you very much.